I'm very excited to have Kelly DeRango here today. He's going to work a calculus problem with us. Kelly, would you take a second to introduce yourself?
Yeah, so I'm Kelly DeRango. I'm a math teacher at the Battle Creek Area Math and Science Center. I'm actually a mid-career switcher. I used to be a professor of economics at K College in Western and economic researcher at the Upjohn Institute for about a decade before I decided to switch gears. And so now here I am. And so you can guess why I picked this problem right here about the interaction between supply and demand. So that's what this
Oh,
problem is
very
all
nice.
about. Yeah, I picked this problem because of that reason, and so I'd like to think through it a little bit. And when I work through problems, I like to just sort of write down what seems to be the important features. That allows me to get going a little bit. And then once I have those pieces, see if I can put them together in a way that makes things click. So let's just do that. So we've got a shop and it sells 500 smartphones per week. I'm just going to write that out over here.
Is that anywhere realistic, do you think? Like how many phones do you think a shop would sell?
That's a good question. I don't know. That's a lot per day, right? That's
Yeah.
like 70 per day. I doubt that's true, right?
Yeah.
Um, Maybe an online retailer selling 500 a week seems more reasonable.
Mm. Yeah, that would make more sense.
Yeah. Um, and then the price is 450 each. And I guess the problem says that they did a survey to show that each decrease of $5 on the price results in 10 more smartphones that you sell. So when you decrease the price by $5, that leads to plus 10 in sales. That's the dynamic that we're going to be working with here. So then the question is, what's the price that maximizes your revenue here? And just intuitively thinking about this, we've got like, this is the good part of reducing um, the price, but then because you sell more. Um, but the bad part is that you lose $5 per each one. And so in some ways, this is like a kind of a rectangle, if you think about it. Um, so if you thought of like, this is the quantity that you sell here, and then here is the price. You could make a choice then to lower the price. And what that does is it bumps out your quantity like this. You can kind of see the interaction a little bit.
Oh, I like that way of looking at it a lot.
Yeah, so like you lose that, but then you gain this. And so the question is, you could see if you had like a really, really high price and you were selling like hardly anything at all, like this, that if you lowered the price a little bit, you're going to get a big payoff, right? So at low prices, just whatever low means, right? There's the big payoff right there. And it's clear that the green is much bigger than the red. But there's got to be some point where if you're selling a lot at a very, very low price already, like this, and then you go down by $5, it just kills all of those other sales that you had, and you just get like this tiny bump out here. And so that's a mistake. And the thing about processes like this that I like is that it intuitively it's sort of a continuous process. Yes, it's true that you can only sell one cell phone, but if you think about it as, let's just allow ourselves to imagine selling half a cell phone so we can think of it continuously,
Mm-hmm.
then it's got to be the case that there is some Goldilocks moment in between where you get the red exactly offsets the green. And I probably won't be able to draw that very well, but there's got to be some moment in between there where you get this exact offset, and that's where you want to be. So that's what we're going to try to do to figure out how to model this. So that's the situation here.
Well, I even love just that idea that somehow, of course, there's going to be a balance point because we have this negative and positive effect playing against each other,
You know,
right?
and that is, so I have like this theorem, not theorem, that I use in calculus. And it's just based on doing a lot of calculus problems. And so here's what the theorem is. It's not a theorem, I'm just warning you, but it's just based on doing a bunch of these. And the theorem is either the solution to problems like these, if there's an offset, the solution is in the middle. And so there's offsetting forces here. So that it's going to be in the middle, and in all likelihood, it's going to be exactly in the middle in some sense. We'll see what that means in a
Yeah.
moment.
Well, we've seen in a couple other problems how like nature likes squares, right? When we're
Yes,
thinking
or
about things
perfect spheres.
geometrically, right?
The other one that happens, though, and this is important in economics, is if there's not an offset or a very, very weak offset, then in economics, they call that a corner solution. So, and in math, they would call that a boundary solution, right? So
Right.
the maximum is at the ends of the interval. But in economics, it means, hey, I'm going to produce as much as my factory can possibly produce because that's,
Yeah.
that's what's going on here.
Um,
So, go ahead.
well, I was just gonna say, is there an economics name for that Goldilocks moment you were talking about?
Yes, that would be, this would be where um, the marginal, um, this is not a cost curve. I was going to say where the marginal cost equals the marginal revenue, but I can't think of what this would be in this particular case because the offset is not from an increasing cost.
Right.
This is just where this is actually, if if you think of that minus this,
Mhm.
in economics, that is called marginal revenue, which is that if you increase the number that you're selling, if you thought about it in terms of the opposite way, and in this problem, they're saying, hey, if you lower the price, so you're controlling the price, then how much do you sell? Usually economists think of it the other way, like you want to sell this amount, what's the price you have to offer? If you thought about it in that second way, then this would be sort of the marginal revenue in terms of how much you sell. And to maximize revenue, you want the marginal revenue to be exactly zero, because then you're not able to squeeze any more green benefit out without having too high of a red cost.
Yeah.
So that's what we're going to look at here. And so the thing you would have to know about this is that revenue equals the price that you're able to charge times the quantity that you sell.
Oh, yeah. It's interesting to me how often these calculus problems have kind of a hidden assumption that you know something about just kind of how the situation works.
Right, right. Um, And so we're going to just call the price, let's see here. They don't tell us what the initial price is, do they?
$450. Isn't that what that was?
Oh, there we go. Thank you. So we're going to say the price equals 450, and then let's say minus some value X here. So if X was $50, now we're selling a $400 phone.
Okay.
And then the quantity that we sell at 450, did they say 500 smartphones? But every time we do that and we lower the price, we get 10 more. Um, and so this is the loss from lowering the price.
Oh, but the 10 was if we went down $5.
Oh, that's right. So that's a good catch. Thank you. So per one, then that would be two, if we wanted to think of it that way.
Wait. Can you spell that out for me a little bit more?
Sure. So if we said that for every $5 in reduction, there is 10 extra sold. So that would mean if I wanted to uh, think of like half of that would be like if I lowered the price 2.5, I would get 5 extra sold, and if I actually divided the original both by 5, that would be $1 and then 2 extra sold.
Oh, that makes sense.
Yeah, so that's what I'm gonna model it as over there. But I do want to say to your students, if your students decided to write this as um, for every $5 we get 10, like that, it
Mhm.
would work. It's going to work out exactly the same. That's not going to change anything at all.
Oh,
But
well, that's fascinating. Okay.
yeah, so
Because
but
those are very different functions.
they are.
Yeah.
They are.
Oh, but
Because
it's like we're changing the units. So here X is dollars. And in that other equation you wrote down, X would be like how many $5 increments?
that's right.
Okay.
That's right. So all right, so when we look at this then, the other thing I was going to say, so that's like, this is the red part over here. That's kind of our loss that's
Ah,
going on. And then this is the gain right there. So that's the gain from extra units. Yeah, one of the things that I do miss from the economic analysis of functions is this kind of talk right there almost never happens in calculus class.
yeah.
And it's like, well, what does this mean? That's what that means. In my opinion, that's like an important moment to step back and say, what's the story?
Right.
What's the story of this? So that's the story. So let's,
Yeah,
um,
especially like that from, now we have technology that can do more and more of the stuff that we used to have to do by hand.
right.
And this meaning, but the meaning can only come from us.
Yes. So let's see here. Did I set this up in a not very clever way? I may have.
I don't, how do you mean?
Well, the
I'm always interested in these moments where like um, an experienced problem solver like you is kind of monitoring what they're doing.
mm-hmm.
Um, because that's something we know that experienced problem solvers do. So what was it that caught your eye right now?
Well, usually problems like this end up having a structure where you would say something like A times, let's see, X minus 5A or something like that. Or just to, yeah, just like, A minus, here, I'll do this, A times A minus 5 or something like that.
Mm-hmm.
And the reason why that is really, really handy, I guess you can still see it from there, so that's fine, but is that you see the two roots of this, if this is your function, are going to be A is 0, makes F be 0. And when A is 5, that makes the function 0 as well.
Okay.
And that is really, you can see immediately what's going to be happening because parabolas um, are always symmetric.
Yeah.
And even without the calculus, you can see if that's 0 and that's 5, that's going to be 2.5 right smack in the middle.
Right.
But saying that, we kind of know what the two roots are just looking at that right off the bat. We can see that the revenue will be 0 when the price is $4.50, and it doesn't take a PhD in economics to know that you will get $0 revenue if you don't charge any money.
Yeah.
Right? So there's that. Well, what's the other 0? Right? So so that is going to be over here when no, this is actually, that corresponds to us charging too much.
Right.
Right, that's too much. That's like nobody buys anymore.
Oh, no,
And
no, no. That's because that's X is the dollars we lowered the price.
X is, oh, that's right. You're right. You're right. Okay. Yep. So it lowered the price to 0.
But that
And
must mean the other one's going to be what you were saying.
uh-huh. Yes. And so that would be minus 250.
So if we lower the price negative 250, that means we're trying to sell the phones for $700 a piece.
And nobody buys.
Nobody buys.
Yeah. Yes. So even with, so with this just simple structure here, you can think of drawing your parabola. And the parabola is going to be facing downward. And if you're not convinced by that, if you multiply it out and you just pay attention to what's going on with those x's, you can see it's going to be a minus 2x squared. And that's going to force the parabola down.
That makes sense.
Yeah, and so then we've got our two roots here. So we said this one is minus 250, x equals minus 250, and this other one is x equals positive 450. So right in between them then, let's see, that is going to be, the difference there is 700, so 350 is, you have to go 350 each way to find the middle, and so that middle right there should be 150 if I did it right. So you want to lower the price by $150, just thinking of this as a parabola that captures the offset.
I don't think that's balanced, right? Because it would be 300 up to 450.
Mm-hmm.
But 300 down would be negative 150.
Oh, you're right. You're right. So what was I doing here? I'm trying to find the middle of the average of these two right here, because that's going to be exactly in the middle. So, oh, am I doing the average? Yes, yeah, I'm doing the average. So 450 and then 250. Wow. So 200. So we have to go down 100. No, geez.
Oh, it's at 100.
What's that?
It's because, so 100 is the average of those two.
Uh-huh. So it's at 100, and that's the middle point.
Right.
Did I do that right? See, not using technology is biting me in the rear. This is exactly, these are exactly the kinds of errors I make all the time in my class. So,
Yeah, me
so
too.
go up 350, down 350, that's it. Okay, so that's the solution to this. Now, we didn't use any calculus, but it might be interesting to see how this works out with some calculus. And do you guys, I guess we'll finish the problem here for a second. We haven't quite finished it yet. What price would the smartphone that would should be used to maximize the revenue? So we said X is 100. So our price is 400, 450 minus X. And we said that X star in economics, star means the optimal amount. That's the notation that's used there.
Oh, I like that.
Yeah, so X star is 100. So the price that is the maximal amount in terms of X equals 450 minus 100. And so that's $350 right there.
Okay.
You can tell how much economists maximize and minimize things. They have their own special notation for that, right?
Yeah, that's
So,
nice. And let's see. And so the phones, then, how many would they expect to sell? Would be the 500 plus double that, so 700.
700, yeah.
Yeah. Okay.
Yeah. So, um, so before we even hop to the technology, though, I just want to think about what's going on here. And we said that we have a solution that's right between those two zeros. Um, it's surprising in some ways that it is so symmetrical, but it is.
Yeah,
But
because even when you were drawing the rectangles, I was thinking that, well, the answer is not going to be a square here because it's kind of scaled,
hmm,
right? Because, the cost and the numbers sold isn't a one-to-one like is when in geometry when we're just, measuring area.
yeah, and it works out that way.
Yeah.
Um, just as a sort of a parenthetical note, because I want to just say this for a second here, is that for those of your students who have had econ, they might be thinking this is strange because cell phones are a very competitive market. Um, and so this seller is acting like they have quite a bit of market power here. So it's not a competitive market the same way that selling corn would be, or soybeans, something like that. Um, and so that's just a note. I mean, if you were modeling something like selling soybeans, um, that would be zero. Like, you can lower the price all you want. It doesn't, right? You actually, you would, yeah, if you raise the price, you would not gain anything at all. So, but what I wanted to say here in terms of the derivative, and I'm assuming you've talked about derivatives as a tangent, is that right?
Yep.
Yes, okay. So you can kind of see what the tangent is doing here. So over here, the slope is positive and the slope is positive. And if this is our revenue function over here, r prime of x is bigger than zero means that we're gaining revenue. And when we're over here, the slope is negative over here, which means that as x increases, we're losing revenue. So we're losing revenue.
That makes sense. So we want to find in between those two.
Yeah, and we want, we talked it when we were looking at the rectangles, we said we want to find that sweet spot, the Goldilocks spot. right? And you can see in terms of the derivative that this right here, that is the Goldilocks spot. And that is where that derivative of x exactly equals 0.
Okay.
Yeah.
That's right. And so do economists refer to the derivative of the revenue? Is that the marginal revenue? Or is
That's margin.
marginal revenue kind of like a almost a differential where you factor in kind of how much you've changed the variable?
No, it's called marginal revenue.
Okay.
And then as things get more complicated, then there's more complicated ideas of how it would change. But this is the marginal revenue with respect to price. And it would actually be own price, and its own price because I'm sure your students are aware that prices of a competitor cell phone, that change might affect how much you can sell.
Sure.
Or prices of electricity or something like that might affect how much people want to buy a cell phone. So anyway, that's why the own price is there. But I think that there is a lot going on in this problem, even though it's a relatively simple one. But one of the reasons I picked it too is you see that geometric representation
Hmm.
there, that there are a lot of problems that first year calculus students are asked to analyze that look like the rectangles. Sometimes you'll be asked about a farmer who has to build fences by a river, and the fence costs so much. What's the optimal configuration for three sides of the fence? Doesn't have to build the fence where the river is because cows won't like to swim. How do you do that? Well, that's a geometric problem, right? It has a little bit of a different offset. But the idea that selling things in the market has, in some sense, the same geometry as a fencing problem, and that both of them are related to parabolas. And those parabolas are interesting in the sense that you look at how the tangent line behaves. There's a lot there, and there's a lot of connections between different ideas. And to me, that's like one of the powerful and enchanting things about mathematics is that you can see this almost like a secret structure that is there between these things that seem to be very, very different, and makes it enjoyable, I think.
Yeah, I love that kind of. It's almost like you're abstracting up, like what all these different problems have in common.
Right, right. Yes. So,
Oh, super nice. Well, Kelly, I can't thank you enough for talking over this and picking a problem that you had all this other expertise to shine the light on what's going on. Uh, it was just terrific.
okay, my pleasure, anytime.
Um, that problem is completely solved, right? Excellent mathematical reasoning. It shows kind of in the application sense of our content standard oh 01. It's you solved the problem, you optimized it, you explained. Kelly explained kind of why that's the case. It doesn't show all the calculus we could show. And so what I would love to see from you guys afterwards is, right, so you know the solution. Since we're trying to learn this calculus that goes with it, what would that solution look like in calculus? Okay, so I just came over to GeoGebra online calculator. Um, we know we can find the derivative from there, right? And the function we were working with is if we lower the price by X dollars, we sell um, more than the 500 we were selling by 2 phones for every dollar we lower the price. I wonder, I should have asked Dr. DeRango, but I wonder what those marketing surveys look like. Like, what questions do they ask people to make a prediction? Like, for every dollar you lower, or every $5 you lower the price, you're going to sell 10 more of these. So that's our function right now. The window isn't what we'd like for that. Let's try that zoom to fit option. It's showing up here. Makes sense. X is going. This is pretty good, right? So if we lower the price $450, we can see that that would make $0. If we raise the price, in other words, lower it negative 250, we would raise the price. And then here's the solution that Kelly found, right? $100 if we lower the price to $350, our revenue would be $245,000 a week. That seems like a pretty good business to be in. Okay, but we want to see kind of how calculus would find that same thing. So we can find the derivative exactly, and then this is a function that if we're looking for where is it zero, the way he explained, right? Because it's increasing, it's decreasing. We want to find that sweet spot right in the middle. Well, negative 4 times what plus 400 is equal to 0. It must be 100, right? But we could also solve, because some of the derivatives we get are not going to be that nice. Right? We want to solve this equation, and it tells us that x is equal to 100. Right? So then this would be the calculus piece to add on to that reasoning that Dr. DeRango did. Now, for a content standard, when you're just trying to show your understanding of the problem, you wouldn't necessarily have that long discussion that he and I had over it. But for a mathematical writing, that is an excellent way to approach those writing assignments. The kind of really digging into the problem, seeing how it makes sense, talking about what you're doing and why. That's what kind of the difference is between one of these content standard pieces and moving to mathematical writing. We're really trying to present a whole picture, and you're presenting it not to a professor who can kind of fill in all the blanks, but for a fellow learner, maybe even somebody before they take calculus, to see if they can understand what you're doing and how you're doing it, why you're doing it. Does your answer make sense? Those are some of the things we want to get to. All right, thanks very much, and thanks again to Dr. DeRango for that great discussion.